Hello viewers, I Nilofer Zargam from Jamia Millia Islamia welcomes you to the chapter of finance today. In this chapter we'll discuss some objects in finance that deal with the time value of money such as investments, loans, etc. The chapter can be broadly classified into four categories. The first one, future value for money. Second, present value of the future amount. Future value of an annuity and the present value of an annuity. We'll study about the simple and compound and their examples, and also we'll discuss about the discount, depreciation and annuity. But we must first understand the following concepts before proceeding further. It can be understood when individuals or business institutions borrow money from others for a certain time period. They pay some extra amount of that money which were borrowed from lender, or as a consideration payable for using others' money. The owner of the money is called the lender and the user of that money is called the borrower. The sum borrowed is the lender is called the principal or the sum, and it is denoted by capital P. The money paid for the use of borrowed money is called the interest, and it is denoted by capital I. Interest, when expressed as a percentage of principal, is called the rate of interest, and rate of interest is denoted by small r. Formula of amount is equal to principal plus interest. Simple interest is computed on the principal for the entire or given time period of borrowing, and it has three factors: the principal, the rate of interest per annum, and the time in years. Thus, a simple interest computed by the formula is given as I equals to P into R into T. Okay, let's see an example here. What is the interest on a sum of rupees 1 lakh at 5% simple interest for 3 years? Let's see the solution. We are given here the P, principal amount, that is equal to rupees 1 lakh, rate of interest that is equal to 5% or 0.05, and the time period is given as T, which is equal to 3 years. So I can be calculated as P into R into T, that is equal to 1 lakh into 0.05 into 3, so that is equal to 15,000. Hence rupees 15,000 will be the total interest in 3 years. Now let's see another example here. Find the amount at 6% simple interest of rupees 70,000 due in 11 months. Now let's see the solution. We're given here the principal amount that is equal to rupees 70,000, rate of interest is equal to 6% or 0.06 per annum, and the time period is given as 11 months. Now let's calculate the interest here. Interest is equal to P into R into T, which is equal to 70,000 into 0.06 into 11 by 12, so that is equal to 3,850. Hence the amount due will be equal to principal amount plus the interest, so that is equal to 70,000 plus 3850, which will give you 73,850. Now let's see an example 3. Find the simple interest on rupees 80,000 from May 11, 2001 to September 11, 2001 at 5% per annum. So we see here the time period is of around 4 months. Now let's see the solution here. Here P, the principal amount, is given as rupees 80,000, rate of interest is given as 5% or 0.05 per annum, and time period is 4 months, so that is 4 by 12 years. Now let's calculate the interest here, which is equal to principal into rate into time, so that is equal to 80,000 into 0.05 into 4 upon 12. So that gives us I equals to 1,333.3. Hence, the simple interest is calculated at rupees 1,333.3. Now, let's see the example 4. A person deposited a sum of rupees 1 lakh in a bank. After 3 years, he withdrew rupees 40,000 and at the end of 5 years he received an amount of rupees 75,200. Now find the rate of interest in this case. Now let's see the solution. We're given here the principal amount is equal to rupees 1 lakh. After 3 years, the principal amount is going to be rupees 1 lakh minus rupees 40,000, so that is equal to rupees 60,000. So after 5 years, we see that the amount is equal to rupees 75,200. It's given in the question. The total interest received will be equal to rupees 75,200 minus rupees 60,000, so that is equal to rupees 15,200. Now let the rate of interest is R% per annum here. Now simple interest on rupees 1 lakh for 3 years will be equal to 1 lakh into 3 into R by 100, which will give you rupees 3,000 R. Now simple interest on rupees 1 lakh minus 40,000 for 2 years, so that is equal to 60,000 into 2 into R by 100, which will give you 1,200 R. The total interest will be 3,000 R plus 1,200 R. So that is equal to 4,200 R. So thus we see that 4,200 R is equal to 15,200, or we can say R is equal to 3.61. Hence we have calculated the rate of interest, which is equal to 3.6%. If the interest as it becomes due is added to the principal, and the amount thus obtained forms a principal for the next period, the time period for compounding the interest may be annual, semi-annual, or other regular period of time, and is called as conversion period. The difference between the amount obtained after the last conversion period and the original sum borrowed is called the compound interest for the given conversion periods. Let P be the principal, small r is the rate of interest in percentage per conversion period, and small n is the number of conversion periods. Then the amount after first conversion period will be equal to principal P plus P into R, so that is equal to P into 1 plus R. So principal for the second conversion period will be equal to P into 1 plus R. So interest for the second conversion period will be equal to P into 1 plus R into small r. So amount after second conversion period will be equal to P times 1 plus R plus P times 1 plus R into R. So that is equal to P times 1 plus R to the power 2. Similarly, amount after third conversion period is equal to P times 1 plus R to the power 3. In general, amount after nth conversion period is equal to P times 1 plus R to the power n. Thus, rate of interest R is equal to annual rate of interest divided by number of conversion periods per year. Now, interest is going to be calculated as amount after nth conversion period minus the principal. So that is equal to P times 1 plus R to the power n minus P. So that is equal to P times 1 plus R to the power n minus 1. So compound interest is equal to C dot I, that is represented as compound interest, and that is given as A minus P. Now let's see an example here. If the principal of rupees 5,000 for 2 years at 10%, find the compound interest if compounding is done first annually, second semi-annually, third quarterly, and the last one monthly. Now let's see the solution one by one. Let's see the solution for the first part. Compounding annually means that there is one interest payment period per year. Thus, n is equal to 2 and r is equal to 10%, that is equal to 0.10. So amount is equal to P times 1 plus r to the power 2. So that is equal to rupees 5,000 into 1 plus 0.1 to the power 2. So that is equal to 5,000 into 1.1 square. So that is equal to rupees 5,000 into 1.21, which is equal to 6,050. Now let's see the second part. Compounding semi-annually means that there are 2 interest payment periods per year. Thus, the number of payment periods in 2 years is going to be n equals to 2 into 2, so that is equal to 4. And the rate of interest is 0.10 divided by 2, or we can say 5%. So amount is given as P times 1 plus R to the power 4. So that is equal to rupees 5,000 into 1 plus 0.05 to the power 4. That gives us 5000 into 1.05 to the power 4. So that is equal to 5000 into 1.2155, which is giving us 6077.5. Now let's come to the third part. Compounding quarterly means that there are 4 interest payment periods per year. Thus the number of payment periods in 2 years is n equals to 4 into 2, that is equal to 8, and r is equal to 0.10 divided by 4, which is equal to 0.025 or 2.5%. Therefore, amount can be calculated as p times 1 plus r to the power 8. So that is equal to rupees 5000 into 1 plus 0.025 to the power 8. So that gives us 5000 into 1.025 to the power 8, which is equal to rupees 5000 into 1.2184, which is equal to 6092. Now let's come to the last part. Compounding monthly means that there are 12 interest payment periods per year. Thus, the number of payment periods in 2 years is going to be n equals to 12 into 2, so that is equal to 24, and r is equal to 0.10 divided by 12, so that is equal to 0.00833. So amount can be calculated as p times 1 plus r to the power 24. That is equal to rupees 5000 into 1 plus 0.00833 to the power 24. So that is equal to 5000 into 1.00833 to the power 24. So that is equal to rupees 5000 into 1.22029, which is equal to 6101.45. Now let's come to another example. A certain sum of money is invested at 4% compounded annually. The interest for the second year is rupees 25. Find the interest for the third year. There is the other part of the question. Let's see the solution to the first part. Let P be the principal. Then amount at the end of first year is equal to P times 1 plus 0.04. So that is equal to P times 1.04. Since n is equal to 1 and r is equal to 0.04, amount at the end of the second year is equal to p times 1.04 to the power 2, and amount at the end of third year is equal to p times 1.04 to the power 3. Now interest for the second year will be equal to p times 1.04 to the power 3 minus p times 1.04 to the power 2. But interest for the second year is rupees 25. Therefore, p times 1.04 to the power 3 minus p times 1.04 to the power 2 is equal to 25. That is, p times 1.04 into 1.04 minus 1 is equal to 25, or p times 1.04 into 0.04 is equal to 25. Thus, interest for the third year is equal to p times 1.04 cube minus p times 1.04 square. So that is equal to p times 1.04 square multiplied 1.04 minus 1. That is equal to p times 1.04 square into 0.04. So that is equal to p times 1.04 into 1.04 into 0.04. So that is equal to 25 into 1.04, which gives us rupees 26. If we invested the principal P for n years at an annual interest rate of r compounded m times a year, then the interest rate per conversion period is r by m, and there are mn conversion periods throughout the term of the investment. In other words, at each instant of time, the investment becomes larger and larger. So this is called the continuous compounding or compounding every moment. In such case, we have amount equals to limit m goes to infinity of p times 1 plus r by m to the power mn. So that is equal to limit m goes to infinity of p times 1 plus r by m to the power m by r, the whole to the power rn. So that is equal to limit m goes to infinity of p times 1 plus r by m to the power x and the whole to the power rn. where x is equal to r by m and x goes to infinity as m goes to infinity. That is equal to p e to the power rn. Since limit x goes to infinity of 1 plus 1 by x to the power x is equal to e, small e, where e is the constant whose approximate value is 2.17828. Now let's come to another example. If interest is compounded continuously, at what annual rate will a principal P double in 15 years? Let's see the solution. Let small r be the annual interest rate compounded continuously. Then the amount A is equal to P into e to the power rn, so that is equal to 2p is equal to Pe to the power r into 15 times e to the power rn, or e to the power 10r is equal to 2. Now taking logarithm on both the sides, we get 10r log of e equals to log of 2. So that is r is equal to log of 2 divided by 15 log of e. So that is equal to 0.3010 divided by 15 into 0.4343. So that is equal to 0.3010 divided by 6.5145, which is equal to 0.046 or 4.6%. Hence, the annual rate of interest compounded continuously is going to be 4.6%. When interest is compounded more than once a year, the given annual rate is called nominal rate. The rate of interest which, if compounded annually, would result in the same amount of interest is called as the effective rate. If interest is compounded more than once a year, the effective rate exceeds the nominal rate because at each time of compounding principal becomes more. However, if the interest is compounded annually, there is no difference between the nominal rate and the effective rate. The effective rate of interest, that is denoted by capital E, can be computed by E equals to 1 plus r to the power n minus 1, where r and n are as defined earlier. Now let's see an example here. What is the effective rate of interest if the nominal rate is 5% per annum converted quarterly? There is a second part to the question as well. Find the nominal rate of compounded semi-annually and equivalent to 5% effective. Now let's come to the solution to the first part. R is equal to 0.05 divided by 4, so that is equal to 0.0125. N here is 1 into 4, that is equal to 4. So effective rate is equal to 1 plus r to the power n minus 1. So that is equal to 1 plus 0.0125 to the power 4 minus 1, which is equal to 1.0125 to the power 4 minus 1. So that is equal to 0.0509 or 5.09%. Hence, the effective rate of interest is 5.09%. The second part to the solution, E is equal to 0.05 here, N is equal to 1 into 2, that is 2. So capital E is going to be 1 plus r to the power n minus 1. So we see that E is already given as 0.05. We can equate that. So that is equal to 1 plus r square minus 1. So that gives us 0.05 plus 1, which is equal to 1 plus r square. So that is equal to 1.05 is equal to 1 plus r to the power n. Now 1 plus r will be equal to under root of 1.05. So that is equal to 1.02469. So that gives r is equal to 1 minus 1.02469, which gives us 0.02469. Now let's calculate the nominal rate, which is given here as 0.02469 per 6 months. So that is equal to 0.02469 into 2 per annum. That gives us 0.04938 or 4.938%. Hence, the nominal rate compounded semi-annually is 4.938%. Now, let's see another example. Which is better investment? 3% per year compounded monthly or 3.2% per year simple interest? Let's come to the solution. R is equal to 3% per annum or 3 by 12% monthly. that is R is equal to 0.0025 and N is equal to 12 into 1, which is equal to 12. Now effective rate, which is given as capital E, is equal to 1 plus R to the power N minus 1, which is equal to 1 plus 0.0025 to the power 12 minus 1, which gives us 1.0025 to the power 12 minus 1, which gives us 1.0304 minus 1, which is giving us 3.04%. Since the effective rate of interest is 3.04% is less than 3.2%, simple interest of 3.2% per year is the better investment. Now let's define present value. The present value, capital P, of the annual amount A due at the end of n conversion periods at the rate R per conversion period may be obtained by solving for P. In other words, a sum which is lent to a borrower always amounts to a higher value. The amount of increase depends on the period of loan, rate of interest, and compounding. We can say that the present value is today's value of tomorrow's money discounted at the interest rate. Future value and present value are related to each other. In fact, they are the reciprocal of each other. The equation of present value is P is equal to A by 1 plus R to the power N. So that is equal to A into 1 plus R to the power minus N. So where P is the present value, A is the amount due at the end of n compounding periods at the rate of R per period. So the quantity A times 1 plus R to the power minus N in the above formula is called as the discount factor. That brings us to another example. Find the present value of rupees 15,000 to be required after 5 years if the interest rate is 9%. Let's see the solution. Here A is equal to rupees 15,000, R is equal to 0.09 and N is equal to 5. So A can be calculated as P times 1 plus R to the power N. So that gives us 15,000 is equal to P times 1 plus 0.09 to the power 5. So that implies 15,000 is equal to P times 1.09 to the power 5. That implies 15,000 is equal to P times 1.5386. So that gives P is equal to 15,000 upon 1.5386, which is equal to 9749.122. So that is approximately rupees 9,749. So what is discount? When a reduction allowed on a financial obligation is generally known as a discount. When the value of an obligation is known at some future date, the process of finding its value at some earlier date is called discounting. The present value of an obligation discounted as bank discount is given by P is equal to A times 1 minus D to the power N, where D is the discount rate as percentage per year, P is the proceeds, that is actual amount received by the borrower, A is the amount to be paid back by the borrower, and N is the time, we can say. Now let's see an example. Find the present value and the discount on rupees 1 lakh due in 3 years at 8% rate of discount, convertible semi-annually. Now let's see the solution. A is given as rupees 1 lakh, D is equal to 0.08 divided by 4, which is equal to 0.04, and N is equal to 3 into 2, which is 6. So P is equal to A times 1 minus D to the power N. So that gives us 1 lakh into 1 minus 0.04 to the power 6, which is equal to 1 lakh into 0.96 to the power 6. That is equal to 1 lakh into 0.78276, which is equal to rupees 78,276. And discount is equal to 1 lakh minus 78,276, which will give you rupees 21,724. Now let's see what is depreciation. The value of a machine or an equipment or any other article which is subject to wear and tear decrease with time, the relative decrease in the value of a machine or any other article is called its depreciation. The value of a depreciable asset at the end of its useful life is called the scrap value. The difference between the scrap value and the original cost is known as a total depreciation. In other words, the decrease in the value of assets. It has two methods of computing the annual depreciation. The first method is straight line method. In this method, the annual depreciation of the asset is found by dividing the total depreciation by the number of years in its estimated useful life. So depreciation is equal to C minus S by N, which is equal to W by N. Where W stands for total depreciation, capital S is the scrap value of the asset, and capital C is the original cost, and N is the useful life in years. The second method is reducing balance depreciation. The salvage value is not considered in determining the annual depreciation, but the book value of the asset being depreciated is never brought below its salvage value regardless of the method used. So we see that V1 is equal to V0 times 1 minus R to the power T, where V0 is the original value of an asset, V1 is the depreciated value after T years. Now if R is the annual rate of depreciation here. Now let's see an example. An asset costing rupees 2000 will be depreciated to a scrap value of rupees 160 in 10 years. Now we have to find the rate of depreciation here. Now let's see the solution. We can say that 160 is equal to 2000 times 1 minus R to the power 10. Now taking logarithm on the both sides, we get log of 160 is equal to log of 2000 plus 10 times log of 1 minus R. So that implies that 2.2041 is equal to 3.3010 plus 10 times log of 1 minus R. So that implies log of 1 minus R is equal to 2.2041 minus 3.3010, the whole thing is divided by 10. So that gives you minus 0.12128. So we see that 1 bar 0.8903. So 1 minus R is equal to ND log of 1 bar 0.8903. So that is equal to 0.7767. So we see R is equal to 1 minus 0.7767, which gives us 0.2233 or 22.33%. An annuity is a sequence of payments, usually of the same amount, made at equal intervals of time. The time period between two successive payments is called the payment period or the rent period. Although the word annuity indicates that the payments are annual, its meaning has been broadened to include payments which can be annual, semi-annual, and quarterly or any other fixed length of time. If nothing is mentioned about the period of interval, it is taken to be 1 year. Ordinary annuity is the annuity in which payments are made at the end of each payment period. For example, housing or a car loan. Amount of an ordinary annuity is given as capital S is equal to R times 1 plus R to the power n minus 1, the whole thing is divided by R. So present value of an ordinary annuity is given as capital V, which is equal to R times 1 minus 1 plus R to the power minus n, the whole thing is divided by R. So that brings us to the end. So finally we have learned today the mathematics of finance. We have learned in the script problem concerning simple and compound interest. The present value concepts in the problems of compound interest are separately discussed here. Also, we have studied about the concept of discount and the depreciation of an article. We have also discussed about the concept of amount and that of the present value of an ordinary annuity. Now, important formulas of the chapter have also been discussed in the script. So that brings us to the end of today's episode. So we are finally ending here and we'll see you again. Have a nice time. Bye.